The objective of this demonstration is to use the ODE solver from Python's scientific library. So I would like to solve the equation which governs the radioactive decay of a single nuclide, and later on I will write the structure for the um, the decay chain. Okay. So in the first coding cell, I have written the libraries to be incorporated in the solution. So these are the numerical Python, scientific Python, and a part of that is dedicated to solve ordinary differential equations, and the plot library. This is the definition of derivative function. So dy dt equals minus lambda y. The actual lambda with the alphabet B is reserved in Python for some other purpose. Therefore, that is restricted, that is not allowed. So that is the function definition. And here is the constant lambda, which is the decay constant of the nuclide. The initial condition is provided as a numpy array. Even though it's a single number, single value, the Python solver requires this to be input as a vector. Then the initial time is 0. This is the initial time, starting point in time. And this is the end of the interval. It's the final time. So during this interval, the solution will be sought. And the t-span, this is also a requirement of the solver. It should be defined as a list variable. Then this is optional parameter in the Python solver. However, I have explicitly defined that one. If it is not provided, then Python solver RK45 will automatically define this one by itself, and that is going to be a variable step size. So it looks for the relative accuracy between the RK4 and RK5 methods and controls the error around a certain bound, and then automatically adjust the step size. However, over here I have defined the time vector. So the function is called in this line, and I have reserved a variable solution. It's going to be an object variable from Python. So it will call from ODE, solve initial value problem, the function definition, t-span, the time interval, the initial condition, and the method. There is a class of methods available for several problems, like for stiff differential equations, and for other problems, you have the separate dedicated solvers. And the last one, uh, uh, however, there are many other, there are few other parameters that can be specified. So with this, all the materials are ready. So you can run the cell and it will generate the solution. So the solution vector has been created, in which the time vector is created with the given step size. Okay. The time step was selected with the number of steps. So it is B minus A over number of steps. So It's like 0.2, 0.4, right? Right. It is that the step size is around 2, right? And it is kept fixed. Okay. The solution has been generated and it is called with the solution.y. So it's a matrix, it's array and it's a matrix, even though y can also be stored as a vector. However, the Python library, it generates a matrix. So the values are in the first row, which is specified, which is called with the index 0. So that is the solution for this one. Now let's extend this problem to extend this exercise to a decay chain. So I'm interested here to solve the problem of a decay chain where the daughter is also radioactive. So my equation will be dy1 and dt, and it is only decaying, so it is minus. Okay. It's lambda 1 times y1, and the daughter nuclide, it will be produced by the parent nuclide. So with the plus term, and it will decay with its own decay mod. So lambda 2 times y2. Okay, so these are the equations that we would like to program. This is the decay chain, parent to daughter. So now let's use the Python library to solve this problem. And the only difference is to write the function definition in in the vectorized form. So I define the function. So now I write capital F, T, and Y. So rather, this is also the capital Y. So I write the equation since I'm going to consider the 2. So I write a variable number of equations as numpy dot size of y, right? So if there are 2 variables in y, right? So its size will be 2. So here I'm going to write here the next one. Okay. So I define a vector y prime. So numpy size, numpy zeros, and the size is for number of equations and of type float. Now y prime of 0 is equal to 2 minus lambda 0 times y of 0. Since I can only use the starting index 0. Then y prime of 1 is equal to lambda 0 times y0 and minus lambda 1 times y of 1. So that is the complete thing. And then the function should return the vector y prime. So I have defined a vectorized function. It contains the time values and the vector. So in the capital Y, there are two members. The parent is represented by Y0 and the daughter is represented by Y1. And now it's time to set up the values and initial values and all that stuff, time steps and everything. Okay. So I can pick up the similar stuff that I generated earlier. So let's only consider that the parent is also going to the daughter. So similar kind of stuff and in the consistent pattern. So a similar set will be generated in a consistent way, and then we will explore the solutions. So this is the setup. Okay, lambda, we now require lambda to be specified as two values. So numpy array. So let's consider first value as 0.04 and the second value as 0.2. Okay, this is fine. Y of 0, it is the parent nuclide 0, parent nuclide 1000, and for daughter nuclide, let's assume that it was 0 at the beginning. So initial condition as a numpy array, this time it is vector of decay constants. Okay. Initial time 0, final time t span a b, n steps 100, and time is generated according to the number of steps and the solver. So f is accordingly be replaced by f, and y naught is replaced by this one, right? So consistent, logical, and you can extend everything, right? According to your plot. And it has worked. It has worked. Now let's see the solution set. Solution vector, sorry, object. So this will have two vectors generated and stored in the matrix structure of Y. So first one is the time vector, and you have quite extended Y vector. Well, we have to see that one separately. So I only write sol dot Y. So here you will be able to see. Yes, the first vector was completed here, and then the second vector was generated. We have the access to plot library, so let's use that one. So plt plot the solution vector of time, and from the solution, the parent nuclide is in the first array, and I plot it as red circles. And the second one, well, let's just do that one in separate line. This is for parent nuclide, and for daughter nuclide, it is plt dot plot solution dot time vector solution dot y. Now we have in the first row the daughter nuclide. Okay, the blue and okay stars. This is for the daughter nuclide, right? PLTX label. So it's a time vector, and PLTY label, it is the nuclides concentration and concentration. So I have to use the double quotes, well, to allow this single quote in the text. And then since these are two curves to be plotted on one single graph, there must be the representative legend. So first one is the parent nuclide, and the other is going to be the first daughter. So we are ready to observe that. Okay. Oh, parent was decaying. However, the daughter was decaying at much faster rate. Therefore, you encounter this type of a situation. Now you have the machine ready to serve your job. Just change the values of the decay constants and other things. That is the setup. So let's change this one upside down, 0.2 and 0.04. Run it. Yes, so 0.04. Right. We would like to see in plot, right? So here the parent decay is much faster, and then the daughter is uh, is increasing, right? The concentration of daughter is increasing. So practically both values cannot be equal. Let's make it a bit slower. Decaying parent nuclide. Okay. Okay. So you find different types of the graphs. I think you have seen them in your textbooks and describing this type of problem of decay chains. So that's how we use the facility in Python, Python-based facility from the scipy. So enjoy learning from this great resource. So you can extend that one to three chain problem. You can use any kind of differential equation, and you have to write in consistent structure, and it will serve the job. So with this, we have come to the end of this demonstration. Since all of you have been observing the pain of staying silent, so take a deep breath. It calms the mind.